click record. So we are recording once again. And we're going to talk about the idea now. We're going to move over to the idea that instead of having a numerical variable that's broken up into two groups so we can compare averages, we're going to look at the idea of having categorical variables. So I'm going to pick out a situation. I'm going to talk about population of a mining town. Okay, maybe the mining town has 50,000 people living in it. Happens that it's in Canada. They actually, I think they have one location where they're still mining asbestos in Canada. We go into this mining town and we want to demonstrate that there's an association between asbestos exposure and lung cancer, let's say. So let's say we go into this town and we're going to check all the records and we're going to see whether people had exposure to asbestos or no exposure to asbestos, right? Either they were exposed to it or they weren't exposed to it. They didn't work at the plant or they did work at the plant or the mine or whatever. We're going to want to look at whether those people, whether they contracted lung cancer or whether they did not no lung cancer, didn't contract lung cancer after 30 years 30 years living in that town or something like that. So what are our variables here? We have two variables. One is exposure. Were they exposed to asbestos? Yes or no. What's our other variable? It's whether or not they got lung cancer. They got lung cancer or they didn't get lung cancer. So we have two variables with two values. Okay, remember our diagnostic tests? We did something called contingency tables. We actually made a table with rows and columns, positive and negative tests, whether or not they tested positive or negative, and whether or not they actually had the disease or not. We're going to use those contingency tables again to organize this categorical data. Okay, and I'm gonna open up an Excel file. I think I actually have it open already. I'm not worried about you having this right now. If you want, you can open up Excel. The numbers are going to be pretty simple, so you can actually copy it as I'm doing it. Here we go. Okay, so I'm going to go into this town, and I'm going to randomly sample 500 people. Right? Randomly go all over the town, sample 500 people, and I'm going to survey them. Did you have an exposure to asbestos or not? Turns out 180 people were exposed to asbestos out of that group, and 320 were not exposed to asbestos. 180 worked in the mine, 320 did some kind of other work in that town. Okay, so we have 500 randomly selected people, turned out to be 180 in one group, 320 in the other group. Okay, so now I'm going to go further, and I'm going to ask those 180 people that were exposed, were you ever diagnosed with lung cancer? And these numbers are made up, of course. Okay, and 60 of them say yes, and 120 of them say no. So I'm going to do the same thing with the people that weren't exposed. 70 of them say yes, 250 of them say no. A lot of smokers in this town. High rate of lung cancer, let's say. So now, as it turns out, we have 130 cases of lung cancer out of 500 people, right? Like I said, maybe it's a very high level of smoking here. A lot of people get lung cancer in this place, but they're really bogus numbers. They're just so that we can learn a little bit about this statistic. Okay, so now let me think about this. The overall rate of lung cancer in this community, right? 130 people, random out of 500 randomly selected people, 130 had been diagnosed with lung cancer, right? So what's the prevalence in this community? The prevalence in this community is equal to, let me get this out of the way so I can actually see something here. Prevalence in this community is equal to 130 divided by 500, or 26%, right? So if I say to myself, if there's no association between asbestos exposure and no asbestos exposure and lung cancer, there's no association between it being exposed or not exposed to asbestos and lung disease, let's say lung disease rather than lung cancer. If there's no association, I would expect both of these groups to get it at the same rate, or the average for the population, the prevalence, 26%. So how many of the 180 people that were exposed to asbestos would I expect to get lung cancer? I'm going to say that's equal to 180 times 0.26. I would expect 46.8 people to get it. Obviously, it's not, it's not an even number. You would never get that exact value, but that's what I would expect. Well, how about the 320 that were not exposed to asbestos? If I expected them to get it at the same rate as the whole population, I would expect that I would have this many cases, 320 times 0.26, or 83.2 people. In fact, if you add these two together, it'll add up to 130, right? Because it's got to add up to 130 because they're both 26%. So when you add them up together, it'll be 26% of 500. So what does that leave for the no's? That leaves 180 minus the yeses, and that leaves 320 minus the yeses. Okay, so now I have two separate tables. One table is the actual values that I observed, that I did the survey and I measured. Those are called my observed values, right? The other table is called my expected values. If I didn't expect that, if I expected that there's no difference in the rate of lung cancer, lung disease, whether you're exposed to asbestos or not exposed to asbestos, this is what I would expect the numbers to look like for that, for those 500 people, 180 exposed and 320 not exposed. Pretty simple, right? There's nothing exotic that's going on here. Is everybody comfortable with these two tables? Right? Kind of makes sense? Okay. So now, if there was no, how about you guys online? You guys okay? If there was no association between lung cancer and asbestos exposure, I would expect my expected values to be very close to what I actually observed, right? And if I got a lot more people that were exposed to asbestos that got lung cancer than the rate I would expect, I would start to think maybe lung cancer, maybe lung disease is caused by asbestos, right? So my expectation is that my expected values are going to be the same as my observed values, right? That's my null hypothesis, that there's no association between asbestos exposure and lung disease. Or in other words, the my expected values are equal to my observed values. Now, do I really expect my observed values to be the same exactly as my expected values? No, they can't be. 40, I'm not going to get, if I took 180 people who were exposed to asbestos and, asked them, I'm not going to get 46.8 people with lung disease, right? It's never going to be exactly the same. Sometimes it's going to be a little bit more, sometimes it's going to be a little bit less, assuming that there's no association. In other words, if the exposure were exposure to dandelions rather than asbestos, I'd expect these numbers to be roughly the same as the expected numbers. Well, I want to create a statistic that helps me to understand whether the differences in these numbers are just due to chance to sampling. I just happen to get lucky and get more people, or unlucky and get fewer people that had lung disease in each group, or whether it's due to a real difference in these two exposures and results, right? So it stands to reason the bigger difference between my expected values and my observed values, the bigger the differences are, the more likely that those differences are real and they're due to the exposure, right? Rather than just being due to chance. So I want a number that's going to predict for me whether or not this is a big difference or not. So one of the ways I can do this, I'm going to do this right now. I'm going to say, this 60 is the same number that's down here in my expected values for 46.8. So I'm just going to go over here and I'm going to find the difference between these two. 60 minus 46.8. So the difference is 13.2. Well, 70 versus 82, what's that equal to? That's equal to 70 minus 83.2. Okay, well, how about this difference up here, the nose here? 120 and 133, how big is that difference? That's equal to 120 minus 133.2. The difference there is 13, and the difference here, 250 is equal to 250 minus 236.8. Okay, that difference is minus 32.13.2. Did I make a mistake here somewhere? Wait a second. Yeah, right. Yeah, I screwed up. Hang on a second here. What was it again? If I got that right? One before. Okay. Okay, this one is 20 minus this. Bottom left. Okay, that one's right. Yeah. Oh yeah, this is. What was? It's 70 minus. Oh, yeah, I get it. Got it. B10. Got it. Put the wrong number in there. Okay, so these are the differences, right? So the bigger the differences, the more likely that these things are really different. So I want some of these differences to be big. If I add all these differences up, what am I going to get? I'm going to get zero, right? They're all going to cancel out because some are negative, some are positive. Because instead of being in one spot, they're in another spot. So that doesn't really help me. What did I do with the sum of squares in order to get rid of those negative signs? I squared them, right? Okay, so I'm going to do the same thing right here. I'm going to take each one of these things and I'm going to square it, right? This one is going to be, okay, that are all positive numbers. This one's going to be, this one's going to be, now when I add them up, it's not going to be, it's going to represent the bigger, now when I add them up, the sum of all these numbers, oops, I didn't put an equal sign in there. Sum of all these numbers is going to be some number that's a positive number, that the bigger the differences are, the bigger that number is going to be. The only problem now I have is this number is up in the stratosphere now because I squared everything. So now I'm going to divide it by some of these. I'm going to take these numbers and say to myself, I can't really use them that way because it exaggerates the differences between all these numbers. So I'm going to take each one of these values and to bring it back into reality. Remember, I divided by the sample size before. Now this time, what I'm going to do is I'm going to divide it by one of the values, by the expected values. So I'm going to take each one of these, this number, and divide by the expected value for that cell. And it comes out to something a little bit more reasonable. I'm going to take the expected value for this one, right? I'm going to take this number, divided by the expected value, which is 83, gives me that value. I'm going to take this one here, divide by the expected value for this, and I'm going to take the this square and divide it by the expected value for this cell. Now, when I take the sum of all these, I get a relatively interesting number, smaller number, that's more in line with the differences here. That number 7.86. That number is your value for the chi-square statistic. That's it. That's as hard as this gets. That number that for chi-square, if that number is, if the expected values and the observed values are exactly the same, that number is going to be zero, right? Because there's going to be difference between these two. Zero squared is zero, divided by whatever is still zero. So they're all going to be different. If there's small differences, that number, when I end up with it, is going to be a small number, right? And as the differences get bigger, that number gets bigger. Well, so the formula for what I just did, that number's pretty big, and we're going to find out why in just a second. You jumped the gun a little bit. That's what I just did. Chi-square, chi is like figure X, Greek letter, figure X, capital X. Chi-square is equal to the sum for each one of those cells, for all four cells, the sum of this value for all four cells, the observed values minus the expected values squared over the expected values. You just do that 4 times. Now, had there been more than 4 cells, for instance, you could have you could have had uh, asbestos exposure, zinc exposure, no exposure. So you have 3 rows, and disease or no disease, 2 columns. So you could have had a 3 by 2 table with 6 cells, right? So it's not just 2 by 2 tables. You could have more than that. Okay, so now, but it's very common to have 2 by 2 tables. So now the deal is that, okay, that's the formula for chi-square, but what does chi-square mean? Well, chi-square has its own distribution. And this is what the distribution looks like. And what is this distribution telling us? Now, I'm going to make it a little smaller so we can actually see it. What is this distribution telling us? It's telling us as chi-square gets bigger, the probability that you will get that value, that you'll get that big a value of chi-square, if there's no association, is the area to the left of chi-square. So if I go over here to a value of 12, the area to the left of 12 is a very small area, very small probability of getting that big a difference between the expected and the observed values if there's no association between the exposure and the disease, in this case, between the observed and expected. The bigger the chi-square value, the bigger the difference between the observed values and the expected values, the bigger chi-square is going to be. So that means if I look at this distribution for chi-square, notice it's not like a normal distribution, right? In other words, most of the area is down here at the low numbers for chi. Chi is just a one-sided test. The t-test, SPSS is going to call it a two-sided test, not really a two-sided test, right? They're just telling you that you don't have to worry about it being a one-sided test when they say that. Okay, now if chi-square is 12, that might be only a 1% chance of getting a chi-square value of 12 or larger in this distribution. If chi-square is 6, there might be a 20% chance of that happening, of this getting that big a difference when there's really no association between the observed values and the expected values. Right? Well, we would look at 7, but just like before, the problem we have is there's a different chi-square distribution for different degrees of freedom, right? So this might not be the right distribution for the number of degrees of freedom that we have. So we need to look up a table that gives us the critical values of chi-square for the number of degrees of freedom that we have. Now, the way that you calculate degrees of freedom for chi-square is you take. Remember, I told you you could have. Let's say that is that you might have more columns and rows than just 2 by 2. Let's say that that you only had 2 by 2. Degrees of freedom are equal to the number of rows minus 1 times the number of columns minus 1. How many rows are there? 2. Rows minus 1 is 1 times the number of columns minus 1. 2 minus 1 is 1. 1 times 1 is 1. 1 degree of freedom. This is considered 1 degree of freedom. So now we have to find the table for chi-square. I'm sorry? Number of rows minus 1 times the number of columns minus 1. R minus 1 times C minus 1. Okay, so in our case, it's 1 times 1. So now I have to find the table. Let me see if I can find it on here. Chi-square. Okay. Here is it. Let me see if I have it on Blackboard. We're going to be going over this in a lot more detail next week and using SPSS to solve. I'm going to show you a quick example of using SPSS to solve it today. But we're going to get into more detail on this stuff. But I'm kind of mishmashing this and throwing a lot of this to you, kind of introducing it and then going over it in more depth, rather than just taking it and just spending one day on one thing, one day on another thing. Because I think you need to get kind of exposed to this so you can start to get some thinking going with what you're going to do with your projects. I'm going to be talking about that very soon. Let's see if I can't find the graph. That's the formula. Come on, let's see. Is that it? So there's a table in here. This stuff you'll be seeing next week. You don't have to worry about this that much right now. Here we go. Here's table. Here's chi-square table. Okay, what do we have here? Degrees of freedom, 1. Okay, if I go across to the area to the right of the critical value, for 1 degree of freedom, the critical value is 3.841. 1 degree of freedom. What was our chi-square that we calculated here? Our chi-square that we calculated here was, remember what it was? Was 7, right? So our null hypothesis is that there's no association between asbestos and lung disease. Our alternative hypothesis is that there is an association. Since for 1 degree of freedom, the critical value is 3.84, and we calculated 7.86, do we reject our null hypothesis? The answer would be yes, because we exceeded the critical value. We're going to have less than 5% chance of being wrong if we say we reject the null hypothesis, there's no association, and say that indeed we accept the alternative, that there is an association. Okay? Yeah, we're going to go over this again on Thursday in more detail. So you will be on the exam along with the chi-square. And analysis variance is going to be the simplest little version of it. Okay? I might just show you a table or something like that. Okay, so we still got Wednesday to go over it. Okay, can you try to post? Oh yeah, I'll get it up as soon as I can. Okay, so at any rate, so that's what we're looking at here when we talk about chi-square. Now I just want to bring up one other thing when we're talking about chi-square. Let me just clear out this area here. The other thing that we look at sometimes when we look at contingency tables like this is we look at something called risk. Okay, what's the risk of getting lung disease if you're exposed to exposure? Well, the risk, as we define it, is equal to the number of people that got lung disease that were exposed to asbestos over the total number of people that were exposed. So the risk is 33%, 0.33. What's the risk of getting lung cancer if you weren't exposed? Well, that's equal to 70 people out of 320 people that weren't exposed. The risk is lower, it's only 21%. We can actually calculate another statistic called relative risk. Sometimes it's called risk ratio, okay? And that is the risk if you're exposed divided by the risk if you're not exposed. And that gives us the number 1.52. Well, what does that mean? That means that we're 1.5 times more likely to get lung disease if we're exposed to asbestos versus if we're not exposed to asbestos. That's called relative risk. We're 1.52 times as likely to get lung disease if we're exposed to asbestos versus if we're not exposed. Just a ratio 0.33, 33% people that were exposed got lung disease versus 21%, just one over the other. There's another version of this called odds. Oh, it didn't light up. Oh, there we go. It did light up for me. Odds. Well, what are the odds of getting lung cancer if you were exposed to asbestos? Odds are funny things. You go to the track and the odds on a horse are 4-1. That means it's a little bit different. It's not really 4 times as likely. That's saying to you that if the horse ran 5 times, he would lose 4 times and win once. That's what odds of 4-1 mean. And the payoff would be like if you bet $2, you would win $4, right? So you would win $10. Excuse me. So the way we calculate odds is a little bit different. Instead of 60 over 180, it's going to be 60 over 120, right? The odds are that if 180 people, the odds would be out of 180 people, 60 would get lung disease, 120 wouldn't. 60 over 120. So that would be zero point 0.5. And the odds, if you didn't get weren't exposed, would be 70 over 250. Odds would be 0.28. Now, naturally, for risk, what did I do? I divided one by the other to get a risk ratio or relative risk. I'm going to do the same thing. I'll get an odds ratio. What's the odds ratio? 0.5 divided by 0.28. So your odds are 1.78 times as great if you're exposed to asbestos versus if you're not exposed to asbestos. They're very similar. The numbers come out similar. In statistical studies, 0.5 divided by 0.28. It's very similar to the risk ratio, the odds ratio. In studies, in public health studies, they tend to use, if you read studies, they tend to use odds ratio more often than they use risk ratio. But they're kind of another way of looking at the same idea, whether or not the risk is the same or the rate is the same, that you would get the disease based on the exposure. We're going to be working on that on Wednesday. Now we have to figure out what would you say if asbestos doesn't cause lung disease, what would you expect the risk to be, the risk ratio to be? Not zero. You got the right idea, though. Not zero. You'd expect it to be the same, one. In other words, the risk for people that were exposed is the same as the risk for people that weren't exposed. So it would be like 0.33 over 0.33, right? So it'd be the same. And the same for odds ratio. We would expect it to be the same, odds ratio to be 1 also. In this case, it's 1.5, 1.78. And what's the deal there? Well, you might want to, in a lot of statistical studies, in public health studies, they'll give you an odds ratio. Say, oh, children that live in older housing, the odds ratio for lead poisoning for children that live in older housing is 2.3. They are 2.3 times as likely as children that their odds of having lead poisoning are 2.3 times as likely as children that don't live in older housing, okay, of having lead poisoning. But the question then becomes, is that 2.3, is that just by chance that the kids that they sampled, or is it because, or do we have a big enough sample to be able to say, well, that's a significant, it really is different than one. So what you do there is that you're looking for whether or not the 95% confidence interval includes the number one. So in other words, you might say the odds are 1.78, but the 95% confidence interval for that number is really 1.1 to 2.9, let's say. So since it's different, since that whole range is one is outside of that range, you can reject the null hypothesis that the difference is one. So your null hypothesis would be the odds are one. Again, don't worry about that. We're going to get into this more detail later on. Well, why is this important to us? Why am I bringing this up now? The reason why I'm bringing this up now is I'm going to start to talk about the project. Right? And the reason why I'm bringing it up now is because I'm going to see if I can still have this open. Okay, let me just make sure they're all muted here. Okay, the reason why I'm bringing it up now is because, see if I got SPSS here. Oh no, I got to reopen it. The reason why I'm bringing it up now is that I'm going to take a real data set like that, North Carolina birth data, and I'm going to look at some categorical data, right? Categories instead of numerical data, and see if I can analyze it. Okay, so let me find that data again. And I'm going to scan through this stuff and just open this stuff up again. Actually, I'm going to drag it out to the desktop so I know I can get to it easy. Okay. You know, I should have changed to plain background, but it's too late now. Okay, hang on a second. Let me look at these questions here. So exactly right. Muffin's exactly right. We reject the null hypothesis because we've exceeded the critical value. Okay, it's a big enough number that we know that those differences are not due to chance. Now, when you look in the textbook, they're going to talk about something called a continuity correction. Okay, and that is 2x2 tables are kind of prone to error when you calculate the chi-square. And in order to do a more conservative analysis, in order to make up for the fact that like these numbers, like the observed values, you can't have numbers like you do in the expected values where they're half a person or something like that, right? There's a break in continuity. You've got 20 people, 21 people. You don't have anything in between compared to the expected values. For that and for some other reasons, they actually will take the observed minus the expected minus 0.5, half the distance between two numbers, and square that, right? So you're subtracting 0.5 from each value and squaring that. So each cell becomes a smaller number before you square it, and then even a smaller number after you square it. So the chi-square value becomes smaller. For the moment, and there's a lot of good valid reasons to include that continuity correction. SPSS, in fact, does it both ways for you. I'm not, for the moment, I'm not going to ask you to do that. You don't have to worry about that for now. You can, for our calculations for right now, you can ignore the continuity correction. I'm going to say open data. Let me go to my desktop. And open that. There we go. Okay, so there's a lot of data here, including a number of pieces of categorical data. Okay, here we go. I think that's it right now. Okay, so let's take a look at some of this categorical data. Now, here's one piece of categorical data, preemie.